Subscribe to the channel so you don't miss out on any of these videos. Imagine an object so powerful, so intense, that if it came within 1,000,000 miles of Earth, it could wipe out entire cities in the blink of an eye. Now, picture this same object existing light years away from us, silent and invisible until one day, we suddenly detect it as a burst of gamma rays strong enough to outshine every star in its galaxy. That's the kind of universe we live in, filled with some of the strangest objects that defy logic, challenge our scientific understanding, and often leave us with more questions than answers. What's out there in the cosmic depths? What are these bizarre, mysterious objects? And why do they behave in ways that sometimes seem impossible? Let's start by talking about Magnetars. If the name sounds intense, that's because it fits perfectly. A magnetar is a type of neutron star, and neutron stars are already strange enough on their own. When a massive star explodes in a supernova, it can collapse into a neutron star, a superdense object packed with more mass than the Sun but squeezed into an area no bigger than a city. But a magnetar takes things even further. Magnetars have magnetic fields that are 1,000 times stronger than typical neutron stars and 1,000,000,000,000 times stronger than Earth's magnetic field. Just being near one could tear apart anything, including atoms themselves. A magnetar's magnetic field is so strong that it would literally rip the electrons off atoms and stretch anything in its vicinity into long, thin shapes, like spaghetti. And the truly mind-blowing part? Scientists aren't exactly sure why magnetars are so different from other neutron stars. We know they exist, but their origin and behavior remain some of the biggest mysteries in astrophysics. Moving on, let's talk about blazars. Imagine a supermassive black hole sitting at the center of a galaxy, pulling in gas, dust, and entire stars, creating a swirling disk of light and energy. In some galaxies, these black holes spit out enormous jets of radiation that travel across the universe, and when one of these jets happens to be pointed directly at us, we call it a blazar. Blazars are among the brightest and most energetic objects in the universe, and their jets of radiation can reach across billions of light years. But here's the thing, we don't fully understand what powers these jets, or how they're able to remain stable over such vast distances. The intensity of a blazar is also far from constant. Sometimes, they can suddenly flare up, releasing massive amounts of energy for reasons we're only beginning to explore. Scientists think magnetic fields might play a role in these outbursts, but we still don't have a clear picture of the full mechanics behind them. Blazars remind us of the sheer power of the universe and that, even when we think we understand black holes, there's always something new to surprise us. Now, let's dive into an even stranger idea, white holes. Most people know about black holes, which are regions in space where gravity is so strong that nothing, not even light, can escape. White holes, however, are the hypothetical opposites of black holes. Instead of pulling things in, a white hole would push everything away, with nothing able to enter it. Think of it as a cosmic mirror of a black hole. While white holes have been proposed by some scientists as solutions to certain equations in Einstein's theory of general relativity, no one has actually observed one. In theory, a white hole might form when a black hole eventually dies, expelling all the matter it once consumed in a final burst. But this idea is just that, an idea. Without any observational evidence, white holes remain one of the more speculative, mind-bending mysteries of the universe. And then, there are rogue planets. Planets that drift through space without a star to orbit, moving endlessly through the darkness of interstellar space. Normally, we think of planets as orbiting stars, like Earth orbits the Sun. But rogue planets have somehow broken free from their star systems, and they roam through the galaxy on their own. How they become free-floating is still a mystery. Some scientists believe they could be ejected from their original star system during the chaotic early stages of planetary formation, while others think they might form in isolation without a star at all. Rogue planets raise interesting questions. Could they support life, even without the warmth of a star? Some scientists think it's possible that if a rogue planet had a thick enough atmosphere or geothermal activity, it could keep an internal heat source that might allow some form of life to exist, even in the freezing depths of interstellar space. Now let's talk about quasars. Quasars are somewhat similar to blazars but with key differences. They're also associated with supermassive black holes at the centers of galaxies, and they too emit immense amounts of energy. In fact, quasars are so bright that they can outshine their entire host galaxy. What's intriguing about quasars is that they were among the first cosmic objects to reveal just how vast the universe is. Quasars are typically billions of light years away, which means we're seeing them as they were billions of years ago. They provide a glimpse into the early universe, a time when galaxies and stars were still forming. But again, quasars also challenge our understanding of black holes. How can a black hole, which we usually think of as something that swallows everything around it, generate such extreme levels of brightness? It's a paradox that has puzzled scientists since quasars were first discovered in the 1960s. And then, there's something known as fast radio bursts, or FRBs. These are brief, intense bursts of radio waves that seem to come from random locations across the sky. They last just a few milliseconds, but in that time, they can release as much energy as the sun does in a day. FRBs were only discovered in 2007, and their origins are still largely unknown. Some theories suggest they might come from neutron stars or black holes, while others propose even more exotic explanations, like cosmic strings or even alien civilizations. The mystery of FRBs is one of the most tantalizing puzzles in modern astronomy. Some FRBs are one-off events, while others repeat, which adds another layer of complexity to the question of what's causing them. And despite all the advances in our observational technology, we're still left with only theories and no solid answers. Let's also mention the mysterious cosmic voids. These are vast, empty regions of space where there are very few galaxies, stars, or other forms of matter. Some of the largest cosmic voids span hundreds of millions of light years, and they're essentially giant holes in the structure of the universe. Scientists aren't completely sure why these voids exist, but they think they might be a result of the way matter was distributed shortly after the Big Bang. What makes these voids particularly fascinating is that they could hold clues to the fundamental nature of the universe. If we can understand why these empty regions exist, it might help us unravel mysteries about dark matter, dark energy, and the structure of space itself. And speaking of dark matter, this is one of the most enduring mysteries in all of science. We can't see dark matter, we can't touch it, and we can't detect it directly with any of our instruments, yet we know it's there because of its gravitational effects. Galaxies spin in ways that don't make sense if we only consider the visible matter. The missing mass that holds galaxies together and influences the large-scale structure of the universe is what we call dark matter. Scientists estimate that about 85% of the matter in the universe is actually dark matter. But what is it made of? Some theories suggest it might be made up of exotic particles that don't interact with normal matter except through gravity. Others propose that dark matter could be linked to other dimensions or even unknown aspects of gravity. Whatever the case, dark matter continues to be one of the greatest unsolved mysteries in physics and cosmology. Now let's explore dark energy, which is just as mysterious as dark matter, maybe even more so. While dark matter helps hold galaxies together, dark energy does the opposite. It's a force that seems to be pushing the universe apart, causing it to expand at an accelerating rate. Scientists first discovered this unexpected acceleration in the late 1990s, and it was a groundbreaking revelation. Before then, most scientists believed that gravity should be slowing the universe's expansion over time. But instead, galaxies are moving away from each other faster and faster, like there's a hidden force behind it all. We call this force dark energy, and it's estimated to make up about 70% of the total energy in the universe. But what exactly is dark energy? That's where things get murky. Some theories suggest it's an inherent property of space itself, while others speculate that it could be related to quantum mechanics. Some even propose that our understanding of gravity may be incomplete, and dark energy might be pointing us toward a new theory of gravity altogether. The truth is, we're still in the dark about dark energy, and understanding it could revolutionize everything we know about the universe. Then, there's the mysterious phenomenon of antimatter. In many ways, antimatter is the opposite of ordinary matter. Each particle of matter has a corresponding antiparticle with the same mass but an opposite charge. When matter and antimatter come into contact, they annihilate each other in a burst of energy. This isn't just theoretical. We've actually observed antimatter and even created tiny amounts of it in particle accelerators. But here's the problem. According to our best theories, the Big Bang should have created equal amounts of matter and antimatter. If that were true, they would have annihilated each other, leaving behind nothing but energy. And yet, here we are, living in a universe made almost entirely of matter, with hardly any antimatter in sight. This imbalance between matter and antimatter is one of the greatest unsolved mysteries in physics. Why does the universe favor matter? Did something happen early on that tipped the balance? Or is there an entire antimatter universe out there somewhere, mirroring our own? Let's also consider cosmic strings, one of the stranger hypothetical objects predicted by physics. Cosmic strings are theorized to be thin, incredibly dense strings that may have formed in the early universe. Imagine a single line, thinner than an atom but with so much mass that it warps space around it. If they exist, cosmic strings could be billions of light years long, stretching across vast portions of the universe. The idea of cosmic strings comes from certain theories in particle physics and cosmology, and while we haven't observed any directly, their existence could explain some gravitational effects we see on a large scale. Scientists think that if two cosmic strings were to cross each other, they could create powerful bursts of gravitational waves, rippling through the fabric of space-time. Cosmic strings are one of the many theoretical entities that, if discovered, would reshape our understanding of the universe's early history and possibly offer insights into the fundamental forces of nature. Another fascinating mystery in the universe is the concept of the multiverse. The multiverse theory suggests that our universe is just one of an infinite number of universes, each with its own laws of physics, particles, and constants. The idea of the multiverse stems from both quantum mechanics and cosmic inflation theory, which describes how the universe expanded rapidly right after the Big Bang. According to some interpretations, this rapid expansion could have created multiple, bubble, universes, each separate from our own. These other universes might have entirely different physics. Some might contain matter similar to ours, while others could be entirely alien. While we can't observe other universes directly, some scientists believe that subtle patterns in the cosmic microwave background, which is the afterglow of the Big Bang, might offer hints. If proven, the existence of a multiverse would change everything we understand about our place in reality. Instead of a single universe, we'd be part of an unimaginable cosmic landscape where anything that can happen might happen somewhere. Let's dive into black hole singularities, arguably one of the most confounding mysteries of all. We've all heard of black holes as regions where gravity is so strong that not even light can escape, but the core of a black hole, known as a singularity, is something truly mind-boggling. In theory, a singularity is a point where all the matter that falls into a black hole is crushed down to an infinitely small point with infinite density. This concept breaks down our understanding of physics, as the laws of general relativity predict this infinite density, but quantum mechanics suggests it shouldn't be possible. The clash between these two pillars of physics indicates that there's something missing in our understanding. Some scientists believe that a new theory of quantum gravity, which would unite quantum mechanics and general relativity, could solve the mystery of singularities. But until we develop such a theory, black hole singularities remain one of the biggest puzzles in science, pointing to the limits of our knowledge. Another enigma is dark flow, a strange and little understood phenomenon where clusters of galaxies seem to be moving in the same direction at high speeds. This motion can't be explained by the gravitational pull of any visible structures nearby, and it doesn't fit into the standard models of cosmic expansion. Some researchers think dark flow could be caused by gravitational influences from structures beyond the observable universe, meaning there could be unseen forces shaping our universe from outside its visible boundaries. This is one of the more speculative ideas in cosmology, but if dark flow is real and we can understand it, it might give us clues about what lies beyond the edge of what we can observe, a tantalizing prospect that pushes the boundaries of our understanding of the cosmos. And of course, we can't talk about strange cosmic phenomena without mentioning black hole jets. While we know that black holes themselves trap light, some of them also produce powerful jets of particles that shoot out at nearly the speed of light. These jets can extend thousands of light years into space, sometimes forming giant structures that are visible from millions of light years away. What's bizarre is that these jets seem to come from the area around the black hole, not from the black hole itself. Scientists think they might be related to the magnetic fields in the accretion disk of the black hole, but there's still no complete explanation for why or how these jets form. What's even more puzzling is that these jets are highly organized and directional, unlike the chaotic nature we might expect from something as powerful as a black hole. The jets challenge our understanding of black holes and suggest that there's much more going on near these cosmic giants than we currently understand. Then we have the Great Attractor, a massive gravitational anomaly that seems to be pulling our entire galaxy cluster toward it. The Great Attractor is located about 150 million light-years away in the direction of the constellation Centaurus, and it's so massive that it's bending the trajectories of countless galaxies toward it. The problem is, it's located in an area of the sky that's heavily obscured by dust and stars, making it extremely difficult to observe directly. We're not sure what it is or why it has such a powerful gravitational influence. Some scientists think it might be an enormous supercluster of galaxies, while others propose it could be something even stranger. Whatever it is, the Great Attractor is another reminder that there are forces and structures out there that we haven't fully grasped. The Boötes Void is another example of a cosmic oddity that defies easy explanation. This is a vast, empty region in space that's roughly 330 million light-years across and contains far fewer galaxies than expected. While space is mostly empty to begin with, the Boötes Void is an extreme case, almost like a cosmic desert. Some scientists suggest that it could be the result of cosmic processes that pushed matter away from this region early in the universe's history, but there's no definitive answer. The Boötes Void stands as a silent, eerie reminder that the structure of the universe is anything but uniform, with massive gaps that challenge our assumptions about how galaxies and matter should be distributed. LTs consider the idea of vacuum decay one of the most unsettling theories in theoretical physics. It suggests that our universe might exist in a false vacuum state, which is a stable state but not the most stable possible. If a transition to a true vacuum were to occur, it could create a bubble of true vacuum that would expand at the speed of light, effectively wiping out everything in its path. Vacuum decay is purely theoretical and would require very specific conditions to actually happen, but the fact that it's even possible is unsettling. This scenario might sound like science fiction, but it's grounded in real physics, and it reminds us of the fragile nature of the universe as we know it. The universe is filled with phenomena that don't just stretch our understanding but often outright defy it. Each of these strange objects and theories challenges our view of reality, suggesting that the cosmos is far stranger and more complex than we could have ever imagined. And the more we learn, the more questions we uncover, proving that the universe is still full of mysteries waiting to be solved. Let's take a deeper dive into something even stranger, the possibility of white holes. In theory, white holes are the opposite of black holes. Instead of pulling everything inward with their intense gravity, white holes would repel matter and energy, essentially spewing it out. If black holes are cosmic traps from which nothing can escape, then white holes are cosmic fountains, expelling matter in all directions. They've never been observed, and they remain a hypothetical concept, but they pop up in solutions to Einstein's equations for general relativity. The idea suggests that just as matter falls into a black hole, it might emerge from a white hole in a different part of space or even a different universe. Some theories propose that black holes and white holes could be connected by wormholes, effectively making them two ends of a cosmic tunnel. This would mean that if you fell into a black hole, you could, in theory, emerge from a white hole somewhere else in the cosmos. But white holes raise enormous questions. For one, they would have to violate the second law of thermodynamics, which states that entropy, or disorder, always increases. A white hole would be an ordered structure that ejects matter, essentially undoing the chaotic effects of a black hole, which doesn't align with how we understand entropy. Furthermore, any matter emitted from a white hole would have to appear spontaneously, seemingly out of nowhere, which goes against our current understanding of conservation laws. The existence of white holes would fundamentally challenge the rules that govern our universe, and it's one of the reasons they remain a theoretical puzzle. Despite the questions, the idea of white holes continues to fascinate physicists because if they do exist, they could offer insights into some of the biggest mysteries in cosmology, including the nature of space-time itself. Now let's move on to quasars, one of the most powerful and energetic objects in the universe. Quasars are thought to be the active cores of young galaxies, powered by supermassive black holes consuming massive amounts of matter. As matter falls into these black holes, it heats up to incredibly high temperatures, emitting enormous amounts of light and energy in the process. Quasars can be so bright that they outshine their entire galaxy, making them visible across billions of light years. When quasars were first discovered, scientists were puzzled. These objects were so far away and emitted so much energy that it seemed almost impossible for them to exist. It's only with advancements in telescopes and physics that we've come to understand how they work, yet they're still far from fully understood. For example, scientists are still trying to determine why some black holes produce quasars while others don't. Another fascinating aspect of quasars is that they're essentially time capsules from the early universe. Because they're so far away, the light we see from them took billions of years to reach us. This means that by studying quasars, we're looking back in time, observing what the universe was like when it was still young. Quasars also play a role in shaping their galaxies, as the energy they emit can push gas out of the galaxy, potentially affecting star formation. Some theories even suggest that quasars may have contributed to the formation of supermassive black holes in the centers of galaxies. But like so many things in astronomy, each answer seems to lead to even more questions. Pulsars are another kind of cosmic oddity. These are highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation. As they spin, these beams sweep across space like cosmic lighthouses. If one of these beams happens to point toward Earth, we detect it as a regular pulse of light or radio waves, which is why they're called pulsars. The precision of these pulses is mind-boggling. They're so regular that they rival the accuracy of atomic clocks. This regularity makes pulsars incredibly useful for studying the universe. For example, scientists use them to test theories of gravity and to map out the galaxy. Pulsars were first discovered in 1967, and at the time, scientists even wondered if they might be signals from extraterrestrial civilizations because of their regularity. But it turned out to be something even more incredible, a natural phenomenon that we're still learning about today. Then, there are blazars, which are a specific type of quasar. Blazars occur when the jet of a quasar is pointed almost directly at Earth. This alignment makes blazars appear much brighter and more variable than other quasars because we're looking straight down the barrel of their jet. Blazars emit radiation across the electromagnetic spectrum, from radio waves to gamma rays, and they're among the most energetic phenomena in the universe. The power of a blazar is difficult to comprehend. A single blazar can outshine an entire galaxy, releasing energy on a scale that's hard to fathom. Blazars are also highly variable, with their brightness changing dramatically over short periods. This variability is still somewhat mysterious, but it's thought to be related to processes in the accretion disk and the magnetic field surrounding the black hole. Blazars are like cosmic beacons, and their study has led to insights into high-energy astrophysics and the extreme environments around black holes. Let's return to the concept of magnetars, one of the strangest and most extreme types of neutron stars. Magnetars are similar to pulsars, but they have magnetic fields that are hundreds of millions of times stronger than any magnet we could create on Earth. In fact, their magnetic fields are so strong that they can distort the shapes of atoms. If you were to get within 1,000 kilometers of a magnetar, its magnetic field would erase your atoms, literally tearing you apart at the atomic level. Magnetars occasionally release bursts of X-rays and gamma rays, sometimes with so much energy that they can affect satellites and radio signals on Earth, even from thousands of light years away. These bursts are thought to be caused by starquakes on the magnetar's surface, which release energy stored in the magnetic field. Scientists are still trying to understand why some neutron stars become magnetars and why these extreme magnetic fields occur. Magnetars are so strange and powerful that they seem almost like science fiction, yet they're very real. Now let's talk about fast radio bursts, or FRBs. These are extremely brief, intense pulses of radio waves that last only a few milliseconds. FRBs were first discovered in 2007, and since then, astronomers have detected hundreds more, but we still don't know what causes them. Some FRBs appear to come from galaxies billions of light-years away, suggesting they're incredibly powerful events. What's even stranger is that while most FRBs are one-off events, a few of them repeat, sometimes with a regular pattern. The exact cause of FRBs is one of the hottest topics in astrophysics, and there are a variety of theories. Some scientists believe they might be caused by neutron stars or magnetars, while others suggest they could be the result of collisions between massive objects. There's even speculation that they could be signals from extraterrestrial civilizations, although this is considered unlikely by most scientists. Whatever they are, FRBs represent one of the newest and most exciting mysteries in astronomy. One more enigma to consider is the cosmic microwave background, or CMB. This is the faint glow of radiation left over from the Big Bang, and it permeates the entire universe. Discovered in 1965, the CMB is a snapshot of the universe when it was just 380,000 years old, long before stars or galaxies had formed. By studying the CMB, scientists have learned a tremendous amount about the early universe, but it also presents some mysteries. For instance, the CMB is almost perfectly uniform, with only tiny fluctuations in temperature. However, there's an odd anomaly known as the cold spot, a region of the CMB that's significantly cooler than the surrounding areas. Some scientists think this could be a statistical fluke, while others suggest it might be evidence of something more exotic, like a collision between our universe and another universe in the multiverse. The CMB is a relic from the dawn of time, and it's a reminder that even the oldest light in the universe still holds secrets waiting to be discovered. Let's touch on a mystery that's not an object, but rather a phenomenon: cosmic inflation. According to the inflation theory, the universe underwent a brief period of rapid expansion just after the Big Bang, growing exponentially in an unimaginably short period. This inflationary period would explain why the universe appears so uniform on large scales, and why we don't see any large-scale curvature. However, inflation also raises questions that we don't have answers for. For example, what caused inflation to start, and what caused it to stop? Was inflation a one-time event, or could it happen again? Some theories even propose that inflation is still happening in distant regions of the universe, creating new, pocket, universes in an endless cosmic cycle. This concept ties back into the idea of the multiverse, suggesting that our universe might just be one of many created by inflation. But without concrete evidence, inflation remains a theory, one that could hold the key to understanding the true nature of the cosmos. Each of these cosmic phenomena, from white holes to cosmic inflation, challenges the very foundations of our understanding. They reveal a universe filled with forces, objects, and events that defy our current scientific frameworks, suggesting that reality is far stranger and more complex than we can fully comprehend. While science has brought us incredible insights into the universe, these mysteries remind us that we're only scratching the surface. And as technology advances, who knows what new mysteries we'll uncover, or if we'll ever truly understand the depths of the cosmos. As we continue to explore the unknown, let's dive into another of the most perplexing phenomena in the universe: dark matter. While it's not an object or a visible entity like a planet or star, dark matter has such a significant presence that it's often referred to as the invisible universe. Scientists have been able to infer its existence through its gravitational effects on visible matter. The most profound mystery surrounding dark matter is that, despite making up about 27% of the universe's total mass energy content, we still don't know what it actually is. All of the matter that we can observe, planets, stars, galaxies, and even black holes, makes up just a fraction of the universe's total mass. The rest is composed of dark matter and dark energy, either of which can be detected directly by current instruments. Dark matter doesn't emit, absorb, or reflect light, making it completely invisible to telescopes. The only way we know dark matter exists is through its gravitational effects. For instance, galaxies spin at speeds that, according to Newton's laws of gravity, should cause them to fly apart. But they don't. Instead, the extra gravitational pull provided by dark matter seems to hold galaxies together. It's as though the visible matter in galaxies is being pulled along by an unseen force. Without dark matter, galaxies wouldn't have enough mass to maintain their structure. There's also evidence that dark matter helps form galaxy clusters and affects the way light travels through the universe, bending it around massive objects. But despite decades of searching, dark matter has yet to be directly observed. Numerous theories abound as to what dark matter might be. Some propose it could be composed of unknown particles like WIMPs, weakly interacting massive particles, or axions, while others suggest that it could be related to modifications in the laws of gravity. The search for dark matter is one of the most significant areas of research in modern physics, and its discovery could revolutionize our understanding of the universe. On a somewhat related note, let's consider the possibility of rogue planets that don't orbit a star. Instead, these planets drift through space, untethered to any central source of light or heat. Rogue planets are some of the most intriguing and elusive objects in the universe. They might be ejected from their home star systems, or they could form in isolation, floating in the cold depths of space. Estimates suggest there could be more rogue planets in our galaxy than there are stars. Yet despite their abundance, rogue planets are notoriously difficult to detect. They don't emit light like stars, and they aren't heated by the energy of a parent star. However, scientists have managed to detect a few rogue planets using techniques like gravitational microlensing, where the gravitational field of a planet can briefly magnify the light of a background star. These rogue planets, drifting alone in the vastness of space, are essentially cosmic wanderers. They pose a fascinating question: if rogue planets exist in such numbers, could any of them support life? Without a star, it seems unlikely, but recent studies suggest that rogue planets could have internal heat generated by tidal forces or radioactive decay, potentially creating the right conditions for life to form. One of the more bizarre and lesser-known phenomena in astrophysics is the concept of cosmic voids. These voids are vast expanses of space that are largely empty, with very few galaxies or other objects within them. Voids can be hundreds of millions of light-years across, and yet they make up a significant portion of the universe's large-scale structure. The existence of these voids has led to some strange and thought-provoking questions. For example, if the universe is expanding and galaxies are spreading out, why do these massive empty spaces exist at all? The discovery of cosmic voids has spurred debates over the underlying structure of the universe, with some researchers even suggesting that these voids may have played a role in shaping the formation of galaxies. Interestingly, some studies have shown that the cosmic microwave background radiation appears to have slight variations in temperature, potentially influenced by these voids. The idea is that as light from the early universe travels through these voids, it might experience slight shifts in temperature, which could have consequences for our understanding of the universe's evolution. Another truly perplexing object is the fast-moving galaxy known as the Hercules Corona Borealis Great Wall. This is the largest known structure in the observable universe, stretching over 10 billion light-years across. The scale of this wall is hard to grasp. It's so vast that it dwarfs everything else around it. The Hercules Corona Borealis Great Wall is a galaxy supercluster, a massive collection of galaxies bound together by gravity. What makes it truly strange is that its size and distribution challenge some of the fundamental assumptions about the cosmos. In particular, it seems to violate the cosmological principle, which states that the universe is homogeneous and isotropic on large scales. That is, it should look roughly the same everywhere. The discovery of such a massive, irregular structure raises important questions about the limits of our understanding of the universe's large-scale organization. If a structure like this can exist, what else might be out there, hidden beyond our observational reach? One of the most mind-bending ideas in modern cosmology is the possibility of the multiverse. The idea that our universe might be just one of many in a vast multiverse of coexisting universes. This concept stretches the limits of imagination, suggesting that beyond the observable universe, there could be an infinite number of other universes, each with its own set of physical laws, constants, and dimensions. While the multiverse theory is still very speculative, it has gained attention due to developments in cosmology and quantum mechanics. For instance, the idea of cosmic inflation, where the universe expanded exponentially in the moments after the Big Bang, could give rise to pocket universes. These universes could have different physical properties, such as varying levels of gravity or distinct laws of physics. Some versions of string theory also suggest the existence of extra dimensions, which could further support the idea of parallel universes. The question remains, can we ever find evidence for the multiverse? If there are other universes out there, how could we detect them? The very existence of multiple universes raises profound questions about the nature of reality itself. Let's move from theoretical to observational mysteries and consider one of the most enigmatic objects in the universe: supermassive black holes. These cosmic giants are thought to exist at the centers of most large galaxies, including our own Milky Way. But despite their name, the true nature of supermassive black holes remains elusive. The current theory is that these objects started out as smaller black holes that grew over billions of years by accumulating matter, but the specifics of this process are still debated. What makes supermassive black holes even more intriguing is their relationship with the galaxies they inhabit. They seem to play a central role in the formation and evolution of galaxies, with their gravitational influence affecting the distribution of stars and the overall shape of the galaxy. However, this relationship remains poorly understood. Some studies suggest that supermassive black holes might even influence the rate at which stars are formed in their host galaxies. This adds another layer of mystery. Are black holes the cause of galaxy formation, or are they simply the product of it? The behavior of these supermassive black holes is still filled with mystery, especially when it comes to their accretion disks. As matter spirals toward the event horizon, it forms an accretion disk, a rotating disk of hot gas and debris. This disk can emit enormous amounts of radiation, but exactly how the energy is released remains a topic of active research. The phenomena observed near supermassive black holes, such as the jets of high-energy particles they emit, further complicate the picture. These jets can travel vast distances, often stretching far beyond the galaxy itself. Some researchers are even looking at the possibility that supermassive black holes might be capable of recycling material in their accretion disks, where matter is continually being ejected and then reabsorbed. If true, this would suggest that black holes might not be as one-way as previously thought, adding yet another layer of complexity to our understanding of these cosmic giants. But black holes don't just come in supermassive sizes, they come in all sizes, and it's possible that there are even primordial black holes that formed in the early universe, before stars and galaxies had even appeared. These black holes would have formed from the collapse of dense regions of matter in the early universe, potentially with masses much smaller than those of typical black holes. The existence of primordial black holes could offer insights into the nature of the early universe, as well as shed light on the mysterious phenomena of dark matter. Some researchers believe that primordial black holes could be a form of dark matter, which would help explain why the invisible stuff is so hard to detect. The search for answers to these cosmic mysteries is ongoing, and the more we learn, the more questions arise. It's clear that the universe is filled with phenomena so strange, so bizarre, and so mind-bending that they challenge everything we think we know about the cosmos. From the energy beams of Magnetars to the wandering nature of rogue planets, these strange objects and concepts are only the beginning of what's out there. What we understand today is only a glimpse of the complexity and wonder that lies in the far reaches of space, waiting for us to uncover its secrets. The universe is far stranger than we can imagine, and the most incredible discoveries are likely yet to come. As we continue to probe the strange corners of the cosmos, we encounter another mind-boggling entity, Magnetars. These are not your average neutron stars. They are one of the most extreme and violent objects in space. Magnetars are neutron stars, which themselves are the remnants of massive stars that have exploded in supernovae. But what sets Magnetars apart is their magnetic fields. While a typical neutron star has a magnetic field that's around 1 trillion times stronger than Earth's, Magnetars have fields that can be up to 1,000 times stronger, making their magnetic fields the strongest known in the universe. To put that into perspective, The magnetic field of a magnetar is so intense that it could tear apart anything as close as 1,000,000 kilometers away, including the atoms of nearby matter. The incredible power of a magnetar's magnetic field can cause the star to emit bursts of high-energy radiation, including X-rays and gamma rays, in what scientists refer to as magnetic flares. These flares are extremely energetic, releasing more energy in a single burst than our Sun does in an entire year. These events are not only fascinating but also dangerous, as they can be lethal to any form of life if close enough. Yet, magnetars are still largely shrouded in mystery. The exact process behind their powerful magnetic fields is not fully understood. One hypothesis is that the magnetar's magnetic field is the result of the collapse of the star's core during its supernova explosion, causing a powerful amplification of the field as it condenses. This amplification process is still a topic of much debate, as it's unclear exactly how such intense magnetic fields can arise and sustain themselves. Magnetars also display some odd behaviors that are yet to be fully explained. For instance, some magnetars have been observed to twist in their behavior, emitting regular bursts of gamma rays and X-rays, but with a frequency that changes over time. This twisting of energy might be the result of complex interactions between the star's magnetic field and the particles that are in its immediate vicinity. Moreover, magnetars are thought to have an incredibly short lifespan in comparison to other stars. The intense radiation and magnetic activity slowly drain the star's energy, causing them to shut down after only a few million years, a blink of an eye in cosmic terms. This short lifespan and their erratic behavior make magnetars one of the most fascinating and unpredictable objects in space, presenting a number of unsolved questions for scientists to tackle. Now let's shift our focus to another phenomenon that blurs the line between what we know and what we don't: blazars. These are a type of active galaxy with a supermassive black hole at its center. What makes blazars so unique is that the jet of particles being ejected from the supermassive black hole is pointed directly at us, making them one of the most powerful and mysterious objects we can observe. Blazars are essentially galaxies that are viewed from an angle where we're looking directly down the barrel of their jets. These jets consist of highly energetic particles moving at nearly the speed of light, emitting vast amounts of radiation across the electromagnetic spectrum, including gamma rays, X-rays, and radio waves. The behavior of blazars is incredibly strange. For one, their radiation is highly variable, sometimes changing in intensity from hour to hour. This means that the material being expelled from the supermassive black hole is moving at speeds that are difficult for scientists to measure accurately. The particles in the jet are accelerated to incredible speeds, so fast that they can travel vast distances across the universe. However, there is still much we don't understand about the physics behind these extreme jets. One of the key questions is how such a large amount of energy is concentrated in such a small space. How do these jets form, and what causes them to emit radiation so intensely? Additionally, the exact mechanism behind the rapid variability of blazar emission is still unclear. Some theories suggest that changes in the density or magnetic fields near the black hole may cause fluctuations in the emission of radiation, while others propose that multiple regions of the jet are emitting radiation independently of each other. Blazars are also connected to a larger mystery in the universe: the nature of active galactic nuclei, AGN. These are the centers of galaxies that are extremely bright and energetic, often powered by the supermassive black holes that reside there. While many galaxies are thought to harbor supermassive black holes at their centers, only some are classified as AGN. What makes the behavior of AGN so perplexing is that they often display immense radiation across the entire electromagnetic spectrum, which suggests that something is going on at the galactic center that we don't yet fully understand. The question remains: what exactly happens in the center of these galaxies to produce such extreme radiation, and why does it happen only in some cases? In addition to blazars, there are other extraordinary phenomena in space that challenge our understanding of the universe. White holes are another such cosmic enigma. If black holes are regions where matter and energy are trapped by an immense gravitational pull, white holes are theorized to be the opposite, regions where nothing can enter, only escape. While black holes are defined by their ability to suck in anything that crosses their event horizon, white holes would theoretically expel matter and energy, making them the exact opposite. However, despite being a fascinating theoretical concept, no white holes have ever been observed. The theory of white holes arises from the equations of general relativity, which allow for the possibility of such objects existing under certain conditions. One suggestion is that white holes could be connected to black holes via wormhole, a theoretical passage between two separate points in spacetime. If this is the case, matter that falls into a black hole could eventually be expelled from a white hole, potentially in another part of the universe. The whole idea of white holes raises fundamental questions about the nature of time, space, and causality. Could these objects exist in a way that we simply cannot yet detect? Are they linked to black holes, or are they entirely separate phenomena? These are questions that remain unanswered, making white holes one of the most tantalizing mysteries of modern physics. Perhaps one of the most bizarre objects to consider in the context of strange and unexplained phenomena is the idea of time crystals. While this is still a theoretical concept, and hasn't been observed in the traditional sense, time crystals have been proposed as a new phase of matter. What's so strange about them is that they would exhibit motion at their lowest energy state, effectively breaking the rules of thermodynamics. In normal systems, when something reaches its lowest energy state, it stops moving. But time crystals, in theory, could exist in a state of perpetual motion, without energy input, for no apparent reason other than their intrinsic quantum properties. They could, in a sense, tick, like a clock without using any energy, violating the usual notion of equilibrium. The theoretical existence of time crystals is the subject of much debate in the scientific community. Could they be an overlooked manifestation of time? If they exist, could they lead to new insights into quantum mechanics and the nature of spacetime itself? All of these strange objects, magnetars, white holes, blazars, and even theoretical concepts like time crystals, pose profound questions about the nature of the universe. They show that the cosmos is far more complex, strange, and elusive than we could ever have imagined. Despite our technological advances and growing understanding of the cosmos, the universe still holds mysteries that challenge our most fundamental concepts of physics, time, and space. As we peer deeper into the universe and uncover more about these bizarre phenomena, it's likely that the greatest mysteries of all are still waiting to be discovered, hidden in the vast, uncharted territories of the cosmos. As we continue to explore these peculiar cosmic objects, it's important to consider the implications they have on our understanding of space and time. The search for answers to the mysteries of magnetars, white holes, and blazars could ultimately lead to breakthroughs in our understanding of the fundamental forces that govern the universe. Each of these strange entities challenges the laws of physics as we know them and forces us to rethink what we understand about the very nature of reality. Take, for example, the phenomenon of cosmic inflation. Cosmic inflation refers to the theory that the universe expanded at an incredibly rapid pace in the first moments after the Big Bang, growing faster than the speed of light for a brief period of time. This theory was proposed to explain some of the strange properties of the universe, such as the uniform distribution of matter across vast distances. While the idea of inflation has been widely accepted, it opens up a host of questions that are yet to be fully answered. Could the bizarre behaviors observed in objects like magnetars and white holes be related to this period of rapid expansion? Could they be remnants of the inflationary epoch, existing in some way as distorted regions of space-time? The link between cosmic inflation and strange objects in the universe is not a direct one, but it's certainly an avenue worth exploring. If inflation had such a profound impact on the early universe, it's possible that some of the most extreme objects in space today, like black holes and magnetars, could be remnants of those early conditions, bearing the imprints of the universe's violent birth. The idea of space-time anomalies is another critical aspect of understanding these strange cosmic objects. In Einstein's theory of general relativity, space-time is a fabric that can be warped and stretched by the presence of mass and energy. We observe this warping in action when we look at the way light bends around massive objects, such as black holes. But what happens when space-time itself begins to behave in ways we don't understand? Could there be regions of the universe where space-time behaves in unexpected ways, perhaps giving birth to phenomena like white holes or causing the strange behavior of Magnetars and Blazars? There are still many unanswered questions about how space-time behaves under extreme conditions. The study of black holes, for instance, has already revealed that the fabric of space-time can be twisted into incredibly strange shapes. But what happens when we push the boundaries even further? Could there be places in the universe where space-time is so severely warped that the usual rules of physics no longer apply? The notion of parallel universes or multiverses also comes into play when considering these bizarre cosmic objects. If space and time can behave in such strange ways, could it be possible that they are connected to realities beyond our own? The theory of the multiverse suggests that there may be multiple universes, each with its own set of physical laws and conditions. Could some of the strange objects we observe in our universe, like Magnetars or white holes, be the result of interactions with these parallel universes? It's a tantalizing idea, but one that remains purely speculative. Still, the possibility of a multiverse provides a framework for thinking about how strange cosmic phenomena might arise and evolve, and whether they could be the product of interactions between universes that exist beyond our perception. Another area of study that is crucial for unlocking the mysteries of these objects is quantum mechanics. Quantum theory, which governs the behavior of particles on the smallest scales, has already given us a radically different view of the universe compared to classical physics. But quantum mechanics is still full of strange and unexplained phenomena. One of the most puzzling aspects of quantum theory is the concept of quantum entanglement, the idea that particles can become linked in such a way that the state of one particle instantaneously affects the state of another, no matter how far apart they are. This phenomenon, which Einstein famously called spooky action at a distance, defies the conventional understanding of space and time. Could some of the weird behaviors of objects like Magnetars or black holes be the result of quantum entanglement on a cosmic scale? And if so, what would that mean for our understanding of the universe and the way the laws of physics operate on large scales? In addition to quantum mechanics, another key area of investigation is dark matter and dark energy. These two mysterious components make up about 95% of the total mass energy content of the universe, yet we have little understanding of what they are or how they interact with normal matter. Dark matter is thought to be responsible for the gravitational effects we observe in galaxies and galaxy clusters, but it does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational influence. Dark energy, on the other hand, is thought to be responsible for the accelerated expansion of the universe. Together, these two mysterious forces could play a role in the strange objects and behaviors we observe in space. For example, could the presence of dark matter or dark energy influence the creation of magnetars or the formation of black holes? Is there a link between the mysterious forces that govern the behavior of dark matter and dark energy, and the bizarre radiation bursts emitted by blazars or the violent flares of magnetars? These questions remain unanswered, but the study of dark matter and dark energy will undoubtedly provide important insights into the nature of the universe and the strange objects that inhabit it. Moreover, the discovery of exotic matter and the possible existence of wormholes could shed light on the nature of strange objects like white holes and black holes. Exotic matter, which is thought to have negative mass and energy, could theoretically be used to stabilize a wormhole, allowing for travel between distant regions of space, or perhaps even between parallel universes. The concept of wormholes arises from the equations of general relativity and suggests that it might be possible to create shortcuts through space-time. But could the strange objects we observe in space, such as blazars, magnetars, and white holes, be related to these theoretical constructs? Could they be the result of interactions with exotic matter or wormholes? While this is still a speculative idea, the study of these phenomena may eventually provide new insights into the nature of space-time and the possible existence of shortcuts through the universe. As we consider the future of astronomical exploration, new technologies and observatories will undoubtedly play a pivotal role in uncovering the mysteries of these strange cosmic entities. Already, space telescopes like the Hubble Space Telescope and the Chandra X-ray Observatory have provided us with a wealth of information about the most distant and extreme objects in the universe. In the coming years, the launch of more advanced telescopes, such as the James Webb Space Telescope, will allow us to peer deeper into the cosmos and potentially discover even more bizarre and unexplained phenomena. These next-generation instruments will help scientists study the behavior of magnetars, black holes, and other strange objects in unprecedented detail. By collecting data on their radiation, magnetic fields, and other properties, astronomers hope to gain a better understanding of the physics behind these cosmic oddities. The universe is filled with strange, perplexing objects that challenge our understanding of space, time, and the fundamental laws of physics. Magnetars, white holes, blazars, and other bizarre phenomena not only reveal the complexity and mystery of the cosmos but also present us with a multitude of unsolved questions. These objects stretch the limits of our imagination and force us to confront the unknown. Whether it's the extreme magnetic fields of magnetars, the mysterious radiation bursts from blazars, or the theoretical existence of white holes, each of these cosmic entities presents an opportunity to learn more about the universe and the forces that govern it. As our technology advances and our knowledge of the cosmos deepens, we will continue to uncover the hidden secrets of the universe, and who knows what strange and astonishing objects lie ahead in the unexplored regions of space. As we continue to delve into the mysteries of the cosmos, the potential implications of understanding these strange objects could reshape our entire perspective on the universe. Imagine being able to unlock the secrets of magnetars and white holes, perhaps finding ways to harness their energy, or better predict their behaviors. Such breakthroughs could lead to advancements in technology, and a deeper understanding of the forces that govern not just our galaxy, but all of space. One of the most exciting aspects of studying these cosmic entities is the possibility that they could hold the key to answering some of the most profound questions about the origins of the universe. Could the violent and strange behavior of magnetars, or the potential for matter to escape from white holes, reveal insights into the very fabric of space and time itself? If we can understand how these objects behave, we may also gain the ability to study the fundamental mechanisms that shape the early universe, perhaps unlocking new theories about the Big Bang or the nature of time before it began. Magnetars are one of the most extreme objects in space. These neutron stars, with magnetic fields trillions of times stronger than Earth's, are some of the most potent forces we know of in the universe. The immense pressure and energy contained within these stars have the potential to unlock answers to questions that have long puzzled scientists. For example, the existence of such powerful magnetic fields in a neutron star challenges our understanding of magnetism. How do these fields form, and why do they remain so strong for such long periods? And when magnetars emit flares, often lasting for seconds or minutes but releasing as much energy as the sun does in a year, what does that tell us about the processes occurring inside them? These incredible bursts of energy, coming from such compact objects, reveal the delicate balance of forces at play within the stars. The fusion of gravity and magnetism on such extreme scales may also provide new insights into how these forces behave under conditions that are otherwise impossible to replicate here on Earth. Imagine using this understanding to better predict the behavior of magnetars or even tap into their energy in a way that could be harnessed for technology in the future. Could magnetars, in some far-off future, become a potential source of power? The concept of white holes introduces an even more intriguing mystery. These theoretical objects are the opposite of black holes, where matter and energy are sucked in and nothing escapes. White holes, in contrast, are said to emit matter and energy. This makes them the reverse of a black hole in every sense, yet there's no conclusive evidence of their existence. Their theoretical nature raises fundamental questions about how the universe works. Could white holes be portals to another part of the universe? Are they connected to the dark matter and dark energy that we have yet to fully comprehend? The idea of a white hole contradicts much of what we understand about the laws of physics. For instance, as matter and energy are supposed to be constrained by black holes' immense gravitational pull, the existence of a white hole would challenge this boundary. If white holes do exist, they might not only be located in distant parts of space but could also shed light on alternate dimensions, time loops, or even the idea of wormholes, which are theoretical passages through spacetime that could create shortcuts between distant parts of the universe. If white holes are tied to such phenomena, they may offer a glimpse into entirely new regions of reality that are presently beyond our comprehension. As for blazars, these objects are another fascinating class of active galactic nuclei. They contain supermassive black holes at their cores, and the black hole's immense gravity pulls the material from the surrounding area. As this material spirals toward the black hole, it heats up and produces powerful jets of energy that shoot out along the poles of the galaxy. These jets are made up of extremely high-energy particles that travel at nearly the speed of light, making blazars some of the brightest and most energetic objects in the universe. The bizarre behavior of blazars and their ability to emit radiation across the entire electromagnetic spectrum, from gamma rays to radio waves, has puzzled astronomers for years. What makes blazars so strange is that they emit their radiation along the axis of the jet, directed straight toward Earth. This alignment makes them extraordinarily bright and allows us to observe them across vast distances. In fact, blazars are so powerful that they can outshine entire galaxies, even though they occupy only a small fraction of space within the galaxy. The mechanisms behind these energetic jets remain elusive. What causes them to shoot out with such force? And how does the supermassive black hole generate the energy needed to power these jets? It's theorized that the accretion disks around these black holes are key to the process. As matter falls into the black hole, it forms a swirling disk of gas and dust that becomes increasingly heated due to friction. The material in this disk is subject to powerful magnetic fields, which can accelerate the particles to nearly the speed of light. These accelerated particles then shoot out along the poles of the black hole in the form of jets. Yet, despite this understanding, many aspects of how these jets form, and why some blazars emit more intense radiation than others, remain a mystery. Another factor contributing to the complexity of blazars is the possible influence of relativity. Due to the high-speed motion of the jets, relativistic effects come into play. As the jet moves toward us at a significant fraction of the speed of light, it appears to brighten and gain more energy due to relativistic beaming. This makes blazars even more challenging to study, as they behave differently depending on the angle from which we observe them. For scientists, this means that the understanding of blazars is intricately linked to both high-energy physics and general relativity. In the realm of strange cosmic objects, rogue planets present yet another bizarre phenomenon. These planets, unlike the ones orbiting stars, drift aimlessly through the galaxy, not bound to any star for light or warmth. They are difficult to detect because they do not emit light of their own, but recent advancements in technology have made it possible to identify them by their gravitational effects or the way they interact with nearby stars. The discovery of rogue planets raises significant questions about planetary formation and the nature of these solitary bodies. How do they form without a star to orbit? Are they the remnants of planets that were ejected from their parent systems, or are they the result of entirely different processes? While rogue planets may be solitary, their existence hints at the possibility of a different type of planetary system, one that is not governed by the traditional rules of stellar formation. These free-floating planets might have unusual chemical compositions, magnetic fields, and atmospheres that could provide a glimpse into planetary conditions that are very different from those on Earth. Could some of these rogue planets harbor life? If so, how would life adapt to the conditions of a planet that receives no light from a nearby star? The discovery of rogue planets has not only expanded our understanding of planetary systems, but has also led to new theories about how planets can survive, evolve, and exist independently of a stellar source. We cannot ignore the vast unknown that still lies in the realm of dark energy and dark matter. These two forces remain some of the greatest cosmic mysteries of our time, and understanding them could revolutionize our entire understanding of the universe. While we know that dark energy is driving the accelerated expansion of the universe, and that dark matter interacts with gravity but not light, the true nature of these forces is still unknown. Could these enigmatic phenomena be tied to the strange objects we observe in space, like black holes or magnetars? Might they be responsible for the bizarre behaviors and extreme properties of objects like white holes or blazars? The universe is full of strange, enigmatic objects that challenge our understanding of physics and the laws that govern the cosmos. From magnetars and white holes to blazars and rogue planets, these objects hold the key to answering some of the most profound questions about the nature of space, time, and reality itself. As we continue to study these cosmic oddities, we move closer to unlocking the deepest mysteries of the universe, and who knows what incredible discoveries lie ahead. The universe is vast, and its secrets are waiting to be uncovered. All we need is the curiosity, the technology, and the drive to keep pushing the boundaries of our knowledge. The strange objects we observe today may be the stepping stones to a deeper understanding of the cosmos, and in that search for answers, the mysteries of the universe may one day be revealed in their entirety. The journey to unlock the secrets of the strangest objects in the universe isn't just an exercise in curiosity. It's also a fundamental pursuit that could ultimately change everything we know about the cosmos. As technology improves, scientists are constantly coming closer to revealing the true nature of these bizarre cosmic entities, and each discovery could lead to a cascade of breakthroughs that reshape how we view space, time, and even the fabric of reality itself. But for now, many of these objects remain mysterious, providing an endless source of fascination and a profound challenge for researchers. One aspect that continues to captivate scientists and astronomers is the mysterious behavior of gamma-ray bursts, GRBs, some of the most energetic explosions in the universe. These bursts can release more energy in a few seconds than our Sun will emit throughout its entire lifetime. Most of these bursts occur in distant galaxies, and they can be detected across vast distances, making them incredibly important for astrophysical research. However, the precise cause of gamma-ray bursts remains uncertain. Two types of gamma-ray bursts have been identified: long-duration bursts and short-duration bursts. Long-duration GRBs are thought to be caused by the collapse of massive stars into black holes, resulting in an enormous release of energy, while short-duration GRBs are believed to originate from the merger of two compact objects like neutron stars or black holes. Yet, despite this basic understanding, the exact mechanisms behind these explosive phenomena remain elusive. How can a single burst release so much energy? And what exactly happens during the collapse of a massive star that produces these bursts? These questions remain at the heart of ongoing research, as scientists try to piece together the intricate processes that govern the behavior of GRBs. Not all strange cosmic phenomena involve explosions or extreme magnetic fields. One of the most perplexing and elusive objects in space is the dark matter halo that surrounds galaxies. We can't see dark matter directly because it doesn't emit, absorb, or reflect light. Yet, scientists have discovered that dark matter exists by observing its gravitational effects on visible matter, such as stars and gas clouds. The most notable of these effects is the way that galaxies seem to spin much faster than expected, implying the presence of an unseen mass. It is estimated that around 85% of the total mass of the universe is composed of dark matter, but we still know very little about its composition. What exactly is dark matter made of? Is it a completely new form of matter that behaves differently from anything we're familiar with? Or could it be related to one of the many exotic particles theorized by physicists, such as weakly interacting massive particles, WIMPs, or axions? The discovery of dark matter halos has opened up a new realm of possibilities in astrophysics, suggesting that much of the universe remains hidden from our direct observation. As we continue to study the effects of dark matter and attempt to directly detect it, we may be on the verge of uncovering one of the most profound mysteries of all. While dark matter is an invisible presence in the universe, another strange object that draws attention is the quasar, an extremely luminous and active galactic nucleus. Quasars are powered by supermassive black holes that consume vast amounts of matter, producing intense radiation in the process. The energy released by these objects is so immense that it can outshine an entire galaxy. In fact, quasars are some of the brightest objects in the universe, and their discovery revolutionized our understanding of galactic activity. But despite decades of study, the specific mechanisms behind their luminosity are still not fully understood. One of the most perplexing features of quasars is the presence of accretion disks, which form around the supermassive black holes that power them. As matter spirals inward toward the black hole, it heats up, emitting incredible amounts of light across multiple wavelengths. This process is thought to be responsible for the intense radiation we observe from quasars. However, the details of how matter in these accretion disks behaves, especially near the event horizon of a black hole, remain a mystery. What exactly happens to matter as it reaches the black hole's point of no return? And why do some quasars seem to emit more energy than others? Another aspect of quasars that remains enigmatic is their connection to the early universe. Some of the most distant quasars observed are believed to be among the first objects to form after the Big Bang. Their extreme brightness makes them ideal tools for studying the early universe, but this raises new questions about the evolution of galaxies and the formation of supermassive black holes. How did these massive black holes form so early in cosmic history? And what role did they play in the development of galaxies? As we explore these strange objects, one thing becomes clear: the universe is full of phenomena that defy our current understanding. From gamma-ray bursts to dark matter halos, quasars to rogue planets, every corner of space seems to hold new surprises, often ones that challenge the very foundations of physics. These objects may seem strange, even alien, but they're integral pieces of the puzzle that astronomers are attempting to solve. To truly grasp the implications of these cosmic mysteries, we must also consider the possibility that some of these objects may be connected to larger-scale phenomena we have yet to fully understand. For instance, the discovery of gravitational waves, ripples in space-time caused by the acceleration of massive objects like colliding black holes, has opened up a new realm of astrophysical exploration. Could gravitational waves be tied to the creation or behavior of magnetars or blazars? Might they be responsible for the intense bursts of energy observed from gamma-ray bursts? And then there's the idea of multiverses, the possibility that our universe is just one of many, each with its own set of physical laws and constants. If this idea is true, it could have profound implications for our understanding of strange objects. For instance, could white holes be gateways to other universes? Or could the behavior of dark matter and dark energy be influenced by the properties of a higher dimensional multiverse? While these ideas remain speculative, they open up exciting possibilities for future research and exploration. One of the most tantalizing possibilities is that the universe may contain even more mysterious objects, phenomena that are beyond our current technological capabilities to detect. As our instruments improve and our understanding of physics deepens, it's entirely possible that we will one day uncover entirely new classes of cosmic entities, each with its own set of strange behaviors and interactions. These new discoveries could reshape our understanding of the cosmos, and perhaps even challenge the very foundations of modern physics. As we continue to observe the most extreme objects in the universe, we can't help but be reminded of just how much we have yet to learn. The strangest objects in space are not just curiosities. They are the keys to understanding the fundamental workings of the universe. Whether it's magnetars with their unimaginable magnetic fields, white holes defying our understanding of black holes, or gamma-ray bursts emitting unimaginable amounts of energy, these objects are pushing the boundaries of our knowledge and prompting us to rethink everything we thought we knew about the cosmos. The answers may not come easily, but the pursuit of these answers will continue to fuel scientific discovery for generations to come. As our instruments become more advanced and our theories evolve, we may one day unlock the mysteries of the strangest objects in the universe. Until then, we remain on the edge of a cosmic frontier, eager to explore the unknown and uncover the secrets hidden among the stars. As we continue to push the boundaries of our knowledge and improve our technology, the quest to understand these strange cosmic entities will only intensify. The tools we have today, such as space telescopes, particle accelerators, and advanced computational models, allow us to peer deeper into the universe and uncover more mysteries, but they also reveal just how much remains out of reach. We are constantly confronted with the fact that there is far more to the cosmos than we can currently comprehend. In our pursuit of understanding magnetars, white holes, gamma-ray bursts, and quasars, it's crucial to acknowledge the role of theoretical physics in guiding our investigations. Concepts such as string theory, quantum mechanics, and general relativity form the backbone of much of the research into these phenomena. For instance, the nature of magnetars' magnetic fields, which can be up to 1,000 times stronger than those of typical neutron stars, might require new approaches to our understanding of electromagnetism at extreme scales. Could there be a deeper, unified theory of forces that would better explain the behavior of such entities? Some scientists believe that the exploration of Magnetars could help answer questions about the unification of forces in the universe. Similarly, white holes, which are the theoretical reverse of black holes, challenge the very essence of what we know about spacetime. While black holes are known for pulling matter in with immense gravity, white holes are thought to expel matter, and theoretically, no matter can enter them. The existence of white holes, though never observed, is an intriguing hypothesis. They are predicted by general relativity in solutions to Einstein's equations, but their connection to black holes is still not well understood. Could white holes be connected to the mysterious wormholes that scientists theorize could exist in the fabric of space? If white holes are real, they might provide a way for matter to travel vast distances across the cosmos, perhaps even connecting distant parts of the universe. Could we someday discover that a white hole is linked to the creation of new galaxies or even new universes? The implications for cosmology would be profound, and exploring such ideas continues to drive research forward. The study of blazars, the ultra-bright and highly energetic objects that are powered by supermassive black holes at the centers of galaxies, is also shedding light on some of the strangest processes in the universe. These active galactic nuclei emit powerful jets of particles at nearly the speed of light, and their ability to produce high-energy gamma rays and X-rays makes them valuable objects of study. Blazars are a special class of quasars in which the jet is pointed directly toward Earth, and their extreme brightness provides a unique window into the most energetic processes in the universe. Despite decades of research, the exact mechanisms that produce the powerful jets in blazars remain a subject of much debate. How do these jets form? Why do they release such massive amounts of energy? Could the intense radiation from blazars offer insight into how galaxies evolve and how the supermassive black holes at their centers grow? As we probe deeper into these cosmic oddities, we find that each discovery raises even more questions. The question of dark energy, for example, has become one of the most significant challenges in modern cosmology. Dark energy is a mysterious force that seems to be accelerating the expansion of the universe, but we still have no clear understanding of what it is. Some theories suggest that dark energy could be linked to quantum fluctuations in space, while others propose that it might be an intrinsic property of the vacuum itself. Could dark energy be the key to understanding the bizarre behavior of objects like white holes or magnetars? Or could it be a fundamental component of the universe's structure, shaping everything from the formation of galaxies to the expansion of space itself? We have only begun to scratch the surface of this mystery. One particularly exciting avenue of research is the study of neutrinos, tiny subatomic particles that interact very weakly with matter. Neutrinos are produced in huge quantities in phenomena like supernovae, gamma-ray bursts, and black hole mergers, and their study could help us understand the fundamental processes at work in these extreme events. Because neutrinos rarely interact with matter, they can travel vast distances through space without being absorbed or scattered, making them an excellent probe of distant cosmic events. By detecting and studying neutrinos, scientists could gain valuable insights into the behavior of objects like magnetars, black holes, and even the processes behind gamma-ray bursts. But detecting neutrinos is an immense challenge, requiring advanced detectors that are often located deep underground to shield them from other forms of interference. Then there's the fascinating possibility that strange objects in the universe could be the result of phenomena that exist beyond our current understanding of physics. Could some of these entities, such as rogue planets, be part of a more complex structure of the universe that we haven't yet discovered? Rogue planets are planets that don't orbit stars and instead float freely through space. These planets are thought to form in the same way as planets around stars, but they end up being ejected from their solar systems or form without a parent star at all. What causes these planets to be cast out into the void? Do they harbor life, or could they be completely barren? The study of rogue planets is still in its infancy, but they could play an important role in understanding the dynamics of planetary formation and the interactions between stars and planets in different environments. As we continue to make new discoveries and push the limits of our knowledge, it becomes clear that we are just beginning to uncover the true complexity of the universe. Each new discovery, whether it's a magnetar, a gamma ray burst, or a rogue planet, adds a new layer to our understanding of the cosmos. However, these objects also raise new questions, and for every answer we uncover, there are countless more mysteries to explore. One of the most exciting aspects of this ongoing journey is the potential for collaboration across scientific fields. As astronomers and physicists work together to study these strange objects, they will need to combine their knowledge of cosmology, quantum mechanics, general relativity, and even fields like computer science and artificial intelligence. The use of AI and machine learning in the analysis of astronomical data, for example, is revolutionizing the way we process and interpret information from telescopes and space probes. AI can help identify patterns in massive data sets that would be nearly impossible for humans to detect on their own, leading to new insights and potentially groundbreaking discoveries. Moreover, as new technologies become available, the ability to observe and study these bizarre objects will only improve. The next generation of space telescopes, such as the James Webb Space Telescope, promises to provide unprecedented views of the cosmos, enabling us to study the birth of galaxies, the formation of stars, and the strange behaviors of exotic objects in greater detail than ever before. These advancements will continue to drive our understanding of the strangest objects in the universe, helping to uncover the answers to some of the most profound questions in science. The strangest objects in the universe, magnetars, white holes, gamma ray bursts, quasars, and beyond, represent the frontier of human knowledge. They push the limits of our understanding and challenge us to rethink everything we know about space, time, and the fundamental forces that govern the universe. The more we learn about these cosmic oddities, the more we realize how little we truly know. But as we continue to explore, study, and observe these mysterious objects, we are one step closer to unraveling the deepest secrets of the cosmos. The universe is full of strange and awe-inspiring phenomena, and with each new discovery, we come closer to understanding our place in the vast, mysterious expanse of space. As we continue to peel back the layers of the cosmos, we uncover more strange and elusive entities that defy conventional understanding. One of the most exciting avenues of space research is the exploration of fast radio bursts, FRBs. These mysterious, high-energy pulses of radio waves were first discovered in 2007, and their origins remain largely unexplained. FRBs last only a few milliseconds, yet they release as much energy as the Sun does in an entire day. They have been detected coming from distant galaxies, far outside our own Milky Way, and their precise cause is still a subject of intense debate. Are they the result of cataclysmic events like the collapse of a neutron star? Could they be the signature of some exotic phenomenon, such as a massive black hole or even a white hole? While some researchers suggest that they could be linked to the merger of neutron stars or magnetars, others hypothesize that they might be caused by aliens using advanced technologies. The mystery surrounding FRBs only deepens as more are detected, and scientists are left grappling with the possibility that these bursts might not be from natural sources at all. Another extraordinary phenomenon is the strange behavior of hypernovae. These are the most powerful supernova explosions in the universe, thought to occur when a massive star collapses into a black hole. Hypernovae release vast amounts of energy, creating incredibly bright and energetic explosions that outshine entire galaxies for a short time. They are capable of producing gamma ray bursts, one of the most powerful phenomena in the universe. The mechanisms behind hypernovae are still not well understood, and many questions remain. For instance, what determines which stars end their lives as hypernovae? And how does the collapse process lead to such a violent explosion? Hypernovae are rare, but their study provides valuable insights into the life cycles of massive stars and the formation of black holes. Could they be the key to understanding the formation of some of the most mysterious objects in the universe, like black holes and neutron stars? The concept of quintessence, a hypothetical form of dark energy that varies throughout space, has also garnered significant interest in recent years. Unlike the cosmological constant, which suggests that dark energy is uniform throughout space, quintessence proposes that dark energy's properties could change over time and across different regions of the universe. This idea challenges our understanding of dark energy, and opens up new possibilities for explaining the acceleration of the universe's expansion. Could quintessence be behind the strange properties of far-flung objects like white holes or magnetars? And if it exists, how does it interact with the fabric of spacetime itself? Another realm of the strange and mysterious is the multiverse theory, which posits that our universe is not the only one. Instead, there could be a vast number of parallel universes, each with its own set of physical laws and constants. This theory could help explain the unusual properties of objects like magnetars, quasars, and white holes. If our universe is just one of many, could these strange entities be common across other universes, with their existence shaped by the differing physical laws that govern each one? Could there be a multiversal connection between phenomena like black holes and wormholes, leading to a deeper understanding of the fabric of reality itself? Meanwhile, the study of wormholes continues to offer tantalizing possibilities. A wormhole is a theoretical passage through spacetime that could create shortcuts for long journeys across the universe. Imagine folding space in on itself, creating a tunnel that allows travel from one point to another in an instant. While wormholes remain a theoretical concept, they could provide the key to unlocking the mysteries of faster-than-light travel, or even serve as a bridge to alternate dimensions or universes. The idea that wormholes might be connected to strange objects like white holes or black holes only adds to the intrigue. If wormholes do exist, could they be used to explore the farthest reaches of space, or perhaps even time travel itself? Perhaps one of the most profound implications of these mysterious phenomena is their potential to reshape our understanding of life in the universe. If strange objects like black holes, magnetars, or gamma-ray bursts could harbor the conditions necessary for life, or even alter the evolution of life across the cosmos, then our assumptions about where life can exist might need to be revised entirely. Could there be forms of life that thrive in the extreme conditions found near these objects, such as on a rogue planet in the wake of a gamma-ray burst or deep within the magnetic fields of a magnetar? These ideas challenge the traditional view of habitable zones around stars and expand the scope of the search for extraterrestrial life. But perhaps the most striking takeaway from studying these strange cosmic objects is the realization that we are still at the very beginning of our cosmic journey. With each discovery, we uncover new questions that push the limits of our imagination. The universe is vast and mysterious, and it's clear that we've only scratched the surface in our quest to understand the forces that govern it. Every new piece of data from telescopes, satellites, and space probes brings us one step closer to unraveling the enigma of the cosmos, but it also reveals just how much we have yet to learn. In the coming decades, as our technological capabilities continue to evolve, we may find that some of these strange objects, like white holes, magnetars, and blazars, are more than just bizarre anomalies. They could hold the key to unlocking some of the deepest secrets of the universe. Could they be the building blocks of new, undiscovered forms of physics? Could they hold answers to questions about the origins of the universe, the nature of dark energy, or the possibility of parallel worlds? The potential for discovery is limitless, and each strange object we uncover only deepens the mystery of the universe's true nature. At the same time, it's important to recognize that these objects also represent the incredible complexity and dynamism of the cosmos. The universe is not a static place. It is a constantly evolving system, where stars are born, die, and transform into exotic entities that challenge our understanding of the laws of nature. Magnetars, white holes, and other strange objects are not just oddities. They are part of the cosmic dance that has been unfolding for billions of years. Each one tells a story about the forces that shape the universe, and each new discovery adds a chapter to that story. The study of these strange entities is not just about understanding isolated objects in space. It's about understanding the universe as a whole. Every new discovery brings us closer to understanding the forces that govern the fabric of spacetime, the nature of energy and matter, and the fundamental laws of physics. And as we continue to explore the farthest reaches of space, we may one day uncover the answers to questions that have plagued humanity for centuries. What is the true nature of time? What happens inside a black hole? Are we alone in the universe? These questions may seem impossible to answer today, but with each strange object we study, we move one step closer to understanding the vast, mysterious cosmos that surrounds us. As we continue to probe the cosmos, we also find ourselves grappling with one of the most profound mysteries of the universe: dark matter and dark energy. While these elusive substances make up around 95% of the universe, they remain completely invisible to our senses and even to most of our instruments. Dark matter, which is thought to account for about 27% of the universe's mass, doesn't emit, absorb, or reflect light, making it undetectable by traditional methods. Scientists have inferred its existence based on its gravitational effects on visible matter, such as the way galaxies spin or how galaxy clusters behave. But the true nature of dark matter remains one of the biggest unsolved puzzles in modern physics. Could it be tied to the behavior of strange cosmic objects like black holes or magnetars? Could it be influencing the strange properties of neutron stars, or even responsible for some of the more mysterious bursts and anomalies we detect from the farthest reaches of space? Dark energy, on the other hand, is thought to make up about 68% of the universe. It is the force behind the accelerated expansion of the universe, a phenomenon that was discovered relatively recently in the late 1990s. This mysterious force seems to be counteracting the pull of gravity and causing galaxies to move away from each other at an ever-increasing rate. What exactly dark energy is, and why it exists, remains one of the greatest unanswered questions in cosmology. Could the behaviors of entities like blazars and quasars be linked to dark energy in some way, perhaps through unknown interactions with the fabric of spacetime? This uncertainty surrounding dark matter and dark energy is one of the reasons why the universe feels like such a mysterious and enigmatic place. Even as we discover strange cosmic phenomena and push the boundaries of our knowledge, we're left with even more questions that challenge our understanding of the very forces that shape the cosmos. One such mysterious object is the neutron star, a stellar remnant left behind after a supernova explosion. Neutron stars are incredibly dense, with masses up to twice that of the Sun packed into a sphere roughly the size of a city. Their extreme density means that a single teaspoon of neutron star material would weigh about 6 billion tons. But perhaps the most intriguing feature of neutron stars is their magnetic fields. These fields are far stronger than anything we encounter here on Earth and are one of the reasons why neutron stars behave in such strange ways. Some neutron stars, called Magnetars, have magnetic fields so intense that they can warp spacetime itself, emitting bursts of gamma rays that are some of the most powerful explosions in the universe. These bursts have puzzled scientists for years. What causes them, and what role does the intense magnetic field of a magnetar play in such violent events? The magnetic fields of neutron stars are so strong that they can affect the behavior of nearby matter, bending light and influencing the orbits of surrounding objects. Some theories suggest that these magnetic fields could be responsible for the formation of certain cosmic jets, which are streams of high-energy particles that shoot out from the poles of some neutron stars and black holes. These jets can extend for millions of light years, and their origins remain a topic of much debate. Could the magnetic fields of neutron stars be channeling this energy, creating some of the most extreme and mysterious objects in the cosmos? In addition to the intense magnetic fields of neutron stars, another phenomenon that has captured the attention of scientists is the event horizon of black holes. The event horizon is the boundary beyond which nothing, not even light, can escape a black hole's gravitational pull. Once an object crosses this threshold, it is doomed to be pulled inexorably toward the black hole's singularity, the point of infinite density at its center. The event horizon represents the ultimate limit of what we can observe and understand about black holes. Any information that falls into a black hole is thought to be lost to the universe forever. At least, that's what classical physics suggests. But quantum mechanics presents a paradox, known as the information paradox, which suggests that information may not be lost, but rather encoded in some way that we cannot yet comprehend. The nature of the event horizon and the singularity at the center of a black hole remains one of the greatest challenges in theoretical physics. If black holes are indeed the end of the line for matter and energy, how do they fit into the larger framework of the universe? Are they gateways to other dimensions, or perhaps to other universes entirely? Some researchers suggest that black holes could act as bridges to wormholes, theoretical passages through spacetime that could allow matter or information to travel faster than light, or even traverse different points in time. Another peculiar aspect of black holes is their connection to blazars, which are active supermassive black holes at the center of galaxies. These black holes are surrounded by powerful jets of material that travel at nearly the speed of light. Blazars are one of the brightest objects in the universe, emitting immense amounts of radiation across the electromagnetic spectrum, from radio waves to gamma rays. Despite their brightness, much about blazars remains mysterious. What causes these jets, and how do they relate to the surrounding accretion disk of gas and dust? Are they linked to the magnetic fields of neutron stars or black holes in ways that we have yet to fully understand? As we study these extreme objects, we begin to see how interconnected they are. The universe is not simply a collection of isolated phenomena, but a vast, interconnected web of forces, particles, and energies. From magnetars to neutron stars, from black holes to the far-flung reaches of space, every discovery brings us one step closer to understanding the underlying fabric of the cosmos. As our technology advances and we are able to observe more distant regions of the universe with greater detail, we will continue to uncover the most bizarre, mind-bending entities imaginable. These strange objects, with their baffling behaviors and unknown origins, are not just puzzles to be solved. They are windows into the deeper workings of the universe itself. In the coming years, as our telescopes peer further into the dark expanse of space and our theoretical models evolve, we may uncover even stranger and more perplexing objects that challenge everything we thought we knew about the universe. Whether it's the elusive nature of dark matter, the unyielding pull of black holes, or the enigmatic behavior of magnetars, we are only scratching the surface of the mysteries that await us. The more we discover, the more we realize just how little we truly understand about the vast, awe-inspiring cosmos that surrounds us. As we journey deeper into the cosmos, there's one more strange and fascinating object that demands our attention: white holes. These theoretical cosmic objects are the reverse of black holes, and their existence, while still speculative, poses some truly mind-boggling questions. While black holes suck in everything that comes too close, including light, white holes are theorized to expel matter and energy in a violent outburst. In some ways, they could be seen as cosmic fountains, objects that eject particles and radiation from their event horizons instead of drawing them in. The concept of a white hole comes from the mathematics of general relativity and is tied to the solutions of Einstein's field equations. In these solutions, the event horizon of a black hole is mirrored by a white hole, theoretically creating a two-way connection between them. This idea leads to speculation that a black hole could potentially be connected to a white hole through a wormhole, forming what is known as an Einstein-Rosen bridge. Such a structure would allow matter to pass from one side of the universe to another, potentially opening up possibilities for intergalactic travel, at least in theory. But could white holes actually exist in our universe, or are they simply an artifact of theoretical physics? Some scientists believe that if white holes do exist, they might only appear under extreme conditions, perhaps linked to the formation of black holes or even the birth of new galaxies. The idea of a white hole remains tantalizing but unproven. In fact, no observational evidence for white holes has been found, and it's unclear if they would even be stable enough to exist in the real universe. Still, the idea of such a phenomenon continues to challenge our understanding of the laws of physics. Could the energy expelled by a white hole form the basis of some of the most unusual cosmic events we observe, like gamma ray bursts, or the energetic jets of quasars and blazars? Or could they be linked to the birth of matter in the early universe, giving rise to new stars, planets, and galaxies? This question brings us to the broader issue of the origins of the universe itself. The Big Bang Theory remains the leading explanation for the origin of the universe, suggesting that the universe began as an incredibly dense and hot point, expanding rapidly in all directions. From this event, all the matter and energy we know today emerged. But if the universe began in such a singularity, could the objects we see in space, black holes, magnetars, and even white holes, be connected to processes that happened in the very first moments of the universe's existence? A key part of this puzzle lies in understanding the singularity, the point of infinite density and curvature that lies at the core of black holes and is theorized to have existed at the origin of the Big Bang. This singularity represents a breakdown of our current physical theories, as general relativity and quantum mechanics cannot fully explain what happens in such extreme conditions. Some theories propose that a quantum description of gravity, still very much in development, could help us bridge this gap, providing a more complete understanding of the universe's beginning and the behavior of objects at the most extreme scales. There are also speculations that the universe itself could be part of a multiverse, an idea that suggests that our universe might be just one of many that exist alongside each other. Some physicists propose that black holes could act as portals to other universes, connecting different realms of existence in a vast and incomprehensible cosmic web. If this is true, then strange objects like black holes, magnetars, and white holes might not be isolated phenomena but rather key players in a much larger and more complex universe, one that we are only beginning to understand. The study of cosmic jets is another fascinating area where the mysteries of space collide with the strange behaviors of cosmic objects. These jets, often seen in connection with supermassive black holes, neutron stars, and magnetars, are powerful streams of charged particles that travel at nearly the speed of light. What drives these jets is still a subject of intense research. In the case of black holes, it is believed that the accretion disk, the swirling mass of gas and dust that orbits the black hole, produces the energy that powers the jets. As matter falls toward the event horizon, it heats up and accelerates, creating a magnetic field that can shoot material away from the black hole's poles in the form of these high-energy jets. Yet, despite this understanding, many questions remain. How exactly do these jets form? And why do some black holes emit jets that stretch for millions of light years? How do the magnetic fields around neutron stars and magnetars play a role in generating these energetic outbursts? And could these jets be somehow linked to the strange and unpredictable behaviors of blazars, whose intense radiation emissions suggest that they may be powered by similar mechanisms? At the farthest reaches of space, there is also the intriguing possibility that the large-scale structure of the universe is not as static as we once thought. Some researchers have suggested that there may be ghost galaxies, or vast, unseen structures lurking beyond the visible universe, galaxies and matter that are too far away or too faint to be detected by our current instruments. The discovery of these hidden cosmic objects would radically change our understanding of how the universe is arranged and how its most unusual entities, such as black holes and magnetars, fit into this grand scheme. This potential hidden structure brings us back to one of the most compelling ideas in cosmology: the cosmic horizon, the limit beyond which we cannot observe. The universe is expanding, and the farther away an object is, the faster it moves away from us. At some point, this expansion will cause distant galaxies, stars, and objects to recede beyond the cosmic horizon, meaning that light from those objects will never be able to reach us. As a result, the universe will seem to be forever expanding and stretching outward, with strange and mysterious objects receding into the distance, forever out of our reach. The idea of the cosmic horizon presents a paradox. As we push the limits of our understanding and technology, we are also confronted with the stark reality that there may always be parts of the universe that we can never observe. Even with the most advanced telescopes, the deepest space missions, and the most sophisticated mathematical models, we may never fully understand the full scope of the universe's strange and mysterious objects. But this doesn't stop us from trying. The search for answers to the questions raised by these bizarre cosmic phenomena is one of the driving forces behind modern astronomy and physics. Every new discovery, every strange new object we uncover, is a piece of the puzzle, a glimpse into a universe that is far stranger and more complex than we could ever imagine. Whether it's the violent behavior of magnetars, the explosive power of white holes, or the strange connection between black holes and dark energy, the universe is full of mysteries that challenge the boundaries of human knowledge. As we continue to explore the strange and unexplained corners of the cosmos, we may one day uncover answers to questions that have baffled scientists for centuries. Until then, the universe remains an infinite source of wonder, mystery, and discovery, urging us to look deeper, think harder, and never stop asking questions. As we continue to delve into the depths of the cosmos, one of the most intriguing aspects of the universe is its inherent chaos and unpredictability. The nature of space is such that even the most carefully crafted theories and models can be upended by unexpected cosmic phenomena. We've already discussed some of the strangest and most bizarre objects in space, but the universe is full of many more mysteries that both surprise and confuse scientists to this day. Among the strangest objects in the known universe are the fast radio bursts, FRBs. These powerful and brief bursts of radio waves last only a few milliseconds, but emit more energy in that short time than the sun will emit in an entire day. Discovered in 2007, FRBs have become one of the most puzzling phenomena in modern astronomy. Some FRBs are so bright that they can be detected even billions of light-years away, and yet their origins remain unclear. Are they caused by highly magnetized neutron stars, or perhaps by exotic events like the collision of black holes or even the interaction of dark matter with regular matter? There's still no consensus on their source, and what makes these bursts even more puzzling is that some of them seem to repeat, while others appear to be one-off events. Could these signals be the result of alien civilizations trying to communicate across the vastness of space? While that's an exciting possibility, the more probable explanation is that they're related to astrophysical processes, like the magnetic fields around neutron stars or the collapse of massive stellar cores. What is perhaps even more confounding is that, in some cases, FRBs have been found to occur in remote and seemingly empty regions of space. These areas of space should be devoid of the usual sources of high-energy radiation, such as massive stars or black holes. So, why are these mysterious bursts appearing in such unlikely places? Could there be unseen objects or forces at work, beyond our current understanding, that are responsible for generating these powerful radio signals? As we try to unravel the mystery of fast radio bursts, we also have to confront the more abstract questions surrounding dark matter and dark energy. Together, they are believed to make up about 95% of the total mass energy content of the universe, yet they remain largely invisible and undetectable by current instruments. Dark matter, which is thought to account for around 27% of the universe, does not emit, absorb, or reflect light, making it completely invisible to telescopes. Its presence is inferred only by the gravitational effects it has on visible matter, like galaxies and galaxy clusters. Without dark matter, the rotation rates of galaxies would be impossible to explain. Similarly, dark energy, an even more mysterious force that constitutes about 68% of the universe, seems to be responsible for the accelerating expansion of the universe. While dark matter exerts an attractive force, dark energy acts as a repulsive force, pushing galaxies apart. This cosmic acceleration is one of the most perplexing phenomena in modern cosmology. Why is dark energy accelerating the expansion of the universe? And why did it not begin to act until billions of years after the Big Bang? The search for dark matter and dark energy is one of the driving forces behind major scientific experiments, like the Large Hadron Collider, LHC, and the Dark Energy Survey. While scientists have managed to detect some indirect signs of dark matter, it's still unclear what it actually consists of. Some theories suggest that dark matter is made up of weakly interacting massive particles, WIMPs, or axions, while others propose that it could be an entirely new kind of matter that we have yet to discover. Similarly, dark energy remains one of the greatest unsolved mysteries in physics. Is it a property of space itself, as some theories suggest? Or could it be linked to a fundamental change in our understanding of gravity and quantum mechanics? Yet another enigma in the cosmos involves the peculiar behavior of blazars, highly energetic and active supermassive black holes at the centers of galaxies that emit powerful jets of radiation. Blazars are among the most luminous objects in the universe, and they have been observed emitting radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. What makes blazars particularly strange is that they appear to emit these jets in a highly focused, narrow beam that is aligned with our line of sight. As a result, they can appear up to 1,000 times brighter than normal galaxies, and their radiation can be incredibly intense. What causes the extreme luminosity of blazars? And why do they seem to be so aligned with our view from Earth? These are questions that remain largely unanswered. Scientists have observed blazars in different wavelengths, trying to study the conditions around their supermassive black holes. Some believe that these jets are powered by the accretion disks of black holes, where matter spirals in at incredible speeds, creating immense heat and magnetic fields. These magnetic fields are believed to channel the matter into highly energetic beams that are ejected from the poles of the black hole. The alignment of the jets with our line of sight may be a result of relativistic effects. Because the jets are moving at nearly the speed of light, they appear much brighter when they are pointed directly at Earth, a phenomenon known as Doppler boosting. Blazars are important objects for understanding the most extreme conditions of the universe, as their radiation provides valuable insights into the behavior of matter under intense gravitational and magnetic fields. However, many questions about their exact mechanics remain unanswered. Are blazars the result of a particular type of supermassive black hole? Or are there other factors at play that determine which black holes will produce such powerful jets? One of the most striking aspects of the study of these strange objects in space is the level of unpredictability that exists in the universe. It's not just the objects themselves that are mysterious, but also the way they behave and interact with one another. For example, some gamma-ray bursts, GRBs, which are extremely powerful explosions in distant galaxies, can release as much energy in a few seconds as the Sun will in its entire lifetime. These bursts are thought to occur when massive stars collapse into black holes or neutron stars, creating a hypernova, a catastrophic stellar explosion. Yet, despite their immense power and brightness, gamma-ray bursts are difficult to predict. While they seem to be associated with particular types of stars, such as those with high masses or rapid rotations, no one knows exactly when or where a gamma-ray burst will happen. Even more baffling is the fact that some gamma-ray bursts seem to be associated with supernovae, while others occur without any visible stellar explosion. This unpredictability is part of what makes the study of space such an exciting endeavor. With every new discovery, scientists uncover more questions than answers. What causes some galaxies to explode with such intense energy, while others remain relatively quiet? Why do certain black holes seem to behave differently than others? And why do objects like magnetars and white holes defy the predictions of our current models? The answers to these questions may one day lead to a more complete understanding of the fundamental forces that shape the universe. As technology advances and our observational tools become more powerful, there's hope that we will one day be able to answer these profound questions. New telescopes like the James Webb Space Telescope and the Square Kilometre Array promise to provide unprecedented views of distant galaxies, black holes, and other cosmic entities, allowing us to explore the universe in greater detail than ever before. Yet, even as we push the boundaries of human knowledge, the mysteries of space will continue to challenge our understanding and inspire new generations of scientists and explorers to venture further into the unknown. The strange objects that populate the universe, magnetars, black holes, white holes, fast radio bursts, and beyond, are not just curiosities. They are windows into the fundamental processes of the cosmos, and they may hold the key to unlocking some of the most profound mysteries of all: the nature of space, time, and existence itself. As we continue to explore these enigmatic entities, we take another step toward understanding our place in the vast and mysterious universe. As we continue our journey through the strange objects that populate the universe, it's impossible to ignore the role of neutron stars, particularly magnetars, in the cosmic drama. Neutron stars themselves are already some of the most extreme objects in the universe, collapsed remnants of massive stars that have gone supernova. These stars are incredibly dense, with masses greater than the Sun, but compressed into a volume no larger than a city. They're so dense that a single cubic centimeter of neutron star material could weigh as much as a mountain. But even among neutron stars, magnetars stand out for their intense magnetic fields, which are several orders of magnitude stronger than those found in typical neutron stars. The magnetic field of a magnetar is so powerful that it can bend the very fabric of space-time around it. The strength of their magnetic fields is so extreme that they can even reshape the atomic structure of materials close to them, potentially ripping atoms apart. These fields are also responsible for the violent bursts of energy magnetars are known to emit, with X-rays and gamma rays being flung out into space with terrifying intensity. It's not entirely clear how such powerful magnetic fields can form, but one leading hypothesis is that it has to do with the supernova explosion itself. During the collapse of a massive star, its core can rotate rapidly, and if the conditions are right, this rotation can result in an extreme amplification of the magnetic field, creating the magnetar. The behavior of magnetars is, without a doubt, bizarre. These stars can suddenly release bursts of energy that can last for only a fraction of a second but can rival the amount of energy that the Sun produces over a span of days or even months. In fact, some magnetars have been observed emitting starquakes, powerful tremors that shake the entire neutron star and can release enormous amounts of energy into space. These bursts of energy are capable of reaching Earth, and astronomers have detected these flashes across vast distances. It's these immense bursts of radiation that make magnetars not only one of the strangest phenomena but also one of the most mysterious. What makes magnetars even more interesting is their unpredictable nature. They don't follow a steady pattern of activity, and the bursts they release are not entirely predictable. It's as if they have their own internal rhythm that doesn't always conform to the laws of physics as we understand them. They can lie dormant for years or even decades before suddenly erupting in an explosion of energy. This raises significant questions about the long-term behavior of these stars. Do they eventually burn out, or do they continue to flare up unpredictably? How does the interaction of magnetic fields and the star's core lead to such dramatic events? Magnetars are a testament to the extreme forces that govern the universe and highlight how much we still have to learn. In addition to magnetars, white holes represent one of the most mind-bending concepts in the realm of cosmology. If black holes are the ultimate cosmic vacuum cleaners, sucking in everything that comes too close, white holes are their theoretical opposites. Instead of pulling matter in, white holes are thought to expel matter and energy from a singularity, forming a sort of reverse black hole. The idea of a white hole arises from the same equations that describe black holes, specifically the Einstein-Rosen bridge, or wormhole, which connects two different regions of space-time. In theory, a white hole could act as the other end of a black hole's event horizon, a place where matter and energy that have fallen into a black hole could theoretically emerge in another part of the universe. However, as intriguing as white holes are, they have never been observed, and their existence remains purely theoretical. Some scientists speculate that white holes might explain certain phenomena, like gamma ray bursts, or the strange behavior of some black hole jets. If white holes did exist, they could provide a means of matter recycling, where material from the inside of a black hole could be expelled into the universe, perhaps to form new stars or galaxies. But for now, these objects remain largely speculative, as there is no direct evidence supporting their existence. The question remains, if white holes do exist, where are they? Could we be looking at the wrong places? Or is there a deeper reason why they haven't been observed yet? The idea of white holes introduces an interesting discussion on the nature of space-time and the Big Bang. Some researchers have even speculated that our entire universe could have been born from the explosion of a white hole. If the Big Bang was, in some sense, the birth of our universe, then could it be that we are living inside what was once a white hole? The concept that the universe could have emerged from a singularity, and is constantly expanding due to the expulsion of energy and matter from that singularity, is one of the more mind-bending ideas to consider. If white holes and black holes are truly interconnected, it raises the possibility that cosmic recycling is a process happening across time and space, where the very fabric of our universe is shaped and reshaped through these extraordinary events. Shifting gears from the theoretical to the tangible, one cannot ignore the remarkable objects that we encounter at the heart of active galaxies, quasars. These incredibly bright and distant objects are powered by supermassive black holes that are actively feeding on surrounding matter, creating intense jets of energy that can outshine entire galaxies. Quasars were first discovered in the 1960s, and their extreme luminosity, often exceeding that of the combined light of all the stars in a galaxy, has made them one of the most puzzling phenomena in space. What causes this incredible brightness? The key lies in the accretion disks around supermassive black holes, where matter spirals inward, becoming heated to millions of degrees as it accelerates toward the event horizon. This intense energy is then released in the form of radiation, creating the blinding light we associate with quasars. One of the most puzzling aspects of quasars is how we are able to observe them at such great distances. Some quasars are located billions of light years away, meaning we are seeing them as they were in the very early universe. This means that we're not just observing a far-off object, but looking back in time to a period when the universe was in its infancy. The discovery of quasars has therefore provided us with an invaluable tool for studying the formation and evolution of galaxies, as well as the growth of supermassive black holes. But as with many other cosmic phenomena, we still don't fully understand what drives the activity of quasars. Could there be other factors at play, such as interactions between galaxies or the presence of dark matter in the surrounding regions? How do these objects evolve over time, and what happens to them once they run out of fuel for their accretion disks? In the broader context of these strange cosmic objects, it's important to recognize that space itself is a vast and incomprehensible place, with mysteries that continue to evade our understanding. Whether it's the enigmatic dark matter that appears to hold galaxies together, the baffling white holes that might be expelling matter across the universe, or the unpredictable and violent behavior of objects like magnetars, the universe is constantly offering up new puzzles for us to solve. And the fact that we don't yet have answers to all these questions only makes the cosmos more fascinating and beautiful. Each new discovery, while it may raise even more questions, is a step toward unraveling the deepest secrets of existence itself. The strange and enigmatic objects we've explored here represent only a fraction of the wonders and mysteries that the universe has to offer. As our technology advances, we continue to push the boundaries of our understanding, uncovering new phenomena that challenge everything we thought we knew about space and time. The journey is far from over, and as we continue to study these cosmic oddities, we may one day find the answers to questions that have plagued humanity for centuries. But for now, these strange objects remain as reminders of how little we still know about the cosmos and the extraordinary forces at work in the universe. As we continue our exploration of the universe's strange and mysterious objects, we must turn our attention to another peculiar class of cosmic phenomena, blazars. These objects are among the most energetic and enigmatic in the universe, and their behavior is unlike anything we observe on Earth. Blazars are a specific type of active galactic nucleus, AGN, a region at the center of a galaxy where a supermassive black hole is consuming surrounding matter. What sets blazars apart from other AGNs is their orientation. They are observed in such a way that the jet of material being expelled from the black hole is pointed directly at us. These jets, made of particles moving at near light speed, are incredibly powerful and can release intense bursts of radiation, spanning the entire electromagnetic spectrum, from radio waves to gamma rays. The exact mechanisms behind the creation of these blazar jets are still a mystery, though scientists believe that the magnetic fields near the supermassive black hole play a crucial role in their formation. The polarization of the light emitted by blazars provides important clues about the behavior of these jets. As the jets of particles move through space, they emit synchrotron radiation, which is polarized. This polarization can tell astronomers about the structure of the magnetic fields within the jets. Blazars are also known for their remarkable variability. They can brighten and fade over timescales of hours to days, making them one of the most dynamic and unpredictable objects in the sky. This variability is often linked to changes in the amount of material being fed into the supermassive black hole, and the interactions of this material with the jets. The strange behavior of blazars is compounded by the fact that they are often located at the very edges of the observable universe. Their immense distance makes them extremely faint, but also incredibly useful tools for studying the nature of space and time. By studying the redshift of blazars, scientists can gain insight into the expansion of the universe and the nature of dark energy, the mysterious force believed to be driving the accelerated expansion of the cosmos. Blazars, in this sense, act as beacons from the farthest reaches of the universe, illuminating our understanding of both the small-scale physics of black holes and the large-scale structure of the cosmos. One of the most intriguing aspects of blazars, however, is their potential connection to high-energy cosmic phenomena, such as cosmic rays. The intense bursts of energy emitted by these objects could be responsible for the production of ultra-high-energy cosmic rays, the most energetic particles in the universe. These cosmic rays, which have energies far exceeding anything produced on Earth, are one of the greatest mysteries in modern astrophysics. Their origins remain unknown, and while some scientists have suggested that blazars might be a source, we have yet to directly observe these particles coming from a specific blazar. The study of blazars and their jets may ultimately help us unravel the mystery of these high-energy particles and their role in the universe. As we shift focus again, we come to another one of the cosmic oddities that has fascinated astronomers for decades: the hypernova. A hypernova is a rare, extremely powerful type of supernova, the result of a massive star collapsing under its own gravity. While typical supernovae occur when stars with masses up to about 8 times that of the Sun explode, hypernovae involve stars that are much more massive, often in the range of 30 to 100 solar masses. These explosions are so powerful that they can outshine an entire galaxy for a short period of time. What makes hypernovae particularly interesting is their association with the formation of gamma-ray bursts, GRBs. GRBs are among the most energetic explosions observed in the universe, and they can release more energy in a few seconds than the Sun will produce over its entire lifetime. Hypernovae are thought to be one possible progenitor for long-duration gamma-ray bursts, which occur when a massive star collapses into a black hole. The core of the star is compressed to such extreme densities that it can no longer support its own mass, and it implodes, releasing a jet of energy that is emitted as a gamma-ray burst. The connection between hypernovae and GRBs has opened up a new area of research in astrophysics, particularly in the study of stellar evolution and the end-of-life behavior of massive stars. Hypernovae are also thought to be important contributors to the production of heavy elements in the universe, such as gold, platinum, and uranium. These elements are believed to be formed during the explosion of the star and are then scattered throughout the surrounding space. Over time, these elements mix with the interstellar medium, enriching it and allowing for the formation of new stars, planets, and even life. Hypernovae, in this sense, play a crucial role in the cosmic cycle of matter, and their study could reveal more about the origins of the elements that make up everything we know. However, despite the immense power and significance of hypernovae, they remain one of the least understood phenomena in astrophysics. How exactly do these explosions occur, and what determines the precise conditions under which a hypernova is produced? How do the different types of massive stars interact with their environment to produce these extreme events? As scientists continue to probe the physics of these stellar explosions, we may uncover more secrets about the nature of stellar death and the forces that govern the universe's most violent events. Moving away from the familiar concept of stars and black holes, we must also address the mysterious phenomenon of fast radio bursts, FRBs. Discovered only in recent years, FRBs are incredibly brief but intense bursts of radio waves that last just a few milliseconds. These bursts are thought to originate from outside our galaxy, though their exact source remains unclear. Initially, FRBs were assumed to be some kind of extraterrestrial communication, a theory that gained some traction given their mysterious and seemingly random occurrence. However, as more and more FRBs were discovered, the scientific consensus began to shift, and it is now believed that the bursts are more likely the result of extreme astrophysical processes. The leading candidates for the origin of FRBs include the merger of neutron stars, the collapse of Magnetars, and even the potential interaction of a black hole with a nearby neutron star. These events are thought to produce immense amounts of energy in the form of radio waves, which we observe as the fast bursts. One of the most puzzling aspects of FRBs is that they appear to follow no predictable pattern. They can occur anywhere in the sky and at any time. Some FRBs repeat, but the intervals between bursts can vary wildly, making it difficult to predict when the next burst might occur. This has led to a growing realization that FRBs could be the result of infrequent, high-energy processes that are not well understood. The study of FRBs is still in its infancy, and researchers are eager to determine exactly what is causing these bizarre bursts of energy. Some have suggested that they could be related to the magnetic fields of neutron stars or even the presence of dark matter. However, Without a more complete understanding of the physics behind FRBs, we can only speculate about their true origins. What is clear is that they represent yet another example of how the universe constantly throws out new, unexpected phenomena that challenge our current understanding of the cosmos. It's important to recognize that these phenomena are more than just curiosities. They are key to unlocking some of the deepest secrets of the universe. From magnetars and white holes to blazars and fast radio bursts, these objects push the limits of our understanding and inspire us to ask even bigger questions. What forces shape the behavior of these cosmic oddities? How do they fit into the broader story of the universe's formation and evolution? And perhaps most importantly, how can we continue to study these phenomena to gain a deeper understanding of the cosmos? The universe is vast, and its mysteries are far from being solved. But each discovery brings us closer to answering the fundamental questions about existence, and in doing so, we uncover more of the cosmic story that surrounds us. The strange objects we've explored here serve as reminders of how much there is left to discover, how much remains hidden beyond the stars. They represent the limits of human knowledge, but also the promise of the unknown, urging us to keep looking, keep questioning, and keep reaching for the stars. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.